Kidders.
Kit Kats. Hi, pumpkins. Are we going to do math? All right. Oh, we're rolling.
We are rolling.
I figured because you had Kitty in there. Hi, calculus students. Welcome to 2.4b examples. You had all the notes you need in 2.4a, but these are some problems I felt you might need some help on. So, number one, here's some hints. When you are asked for a derivative at a given point, find the derivative and input the point right away. It is always easier to simplify values than to simplify functions. So on number 71, 77, etc., it asks you to find the derivative, it gives you the point. Find the derivative, don't clean it up no matter how messy it is. Put that x value in there and clean that up. On number two, let's do number 94 together. Find the second derivative of f of x equals this expression. Now, I know you feel like this would be the quotient rule, and you're welcome to do that. Notice when you take the derivative of the numerator, though, you're going to get 0. So what I tend to do is, again, quotient rule, okay, but in the numerator, when I have a constant, I just write it differently. Let me show you. Here's what I do. Notice I haven't taken the derivative yet. I'm rewriting the function. Here's my constant of 4, and this base of x plus 2 to the third power in the denominator, I'm going to write it as to the negative 3. And now, rather than the quotient rule, I'm just going to use the chain rule here. So here we go. I'm going to take the derivative. I bring along my 4. I bring my negative 3 out front and multiply it. That's negative 12. And reduce the exponent by 1. Right, so that is x plus 2 to the negative 4th. You know what? I'm going to leave it, let's erase a little bit. I'm going to leave it just as x plus 2 to the negative 4th. There you go, times, by the chain rule, the derivative of the inside function. We haven't taken the derivative of x plus 2 yet. It is just a 1, and we really don't need to show multiplying by 1. There we go. Notice they asked for the second derivative. So that is the derivative of the first derivative, would be the second derivative. Here we go. Bringing along my negative 12, going to bring the negative 4 out front and multiply it. That's a positive 48. Going to reduce the exponent by 1. Again, by the chain rule, checking the derivative of that inside function, it is still a 1. And so this is perfectly correct. Or we could write it as 48 over x plus 2 to the 5th in the denominator. Here we go. Asked you to do number 21, 22, and 29. We are not going to completely do these. They're asking for the derivative. I just thought that you might like to see the setup. Okay. Again, you would be fine on number 21 if you use the quotient rule. Notice though, if you take the derivative of the numerator, you're going to get 0. So again, this is what I tend to do rather than go through the whole big quotient rule. I am going to write my expression as 1 over x plus 2 to the 1/2 in the denominator. And I'm going to bring that expression up into the numerator. There we go. And I'm going to take the derivative from there using the chain rule. Number 22, notice what we have is we actually have what would be a quotient inside a square root. The numerator here, again, is a constant. And so I really think this looks kind of messy. I think I can simplify this before I take the derivative. So let's take a look here. Notice, first of all, on the inside, in the denominator, that's t squared minus 2 to the first power. I am going to bring that into the numerator. That would be t squared minus 2 to the negative 1 power. That is underneath the square root. Notice I haven't taken the derivative. I'm just setting it up so it's easier. Notice that this is t squared minus 2 to the negative 1. And I could write the square root as to the 1/2 power. And we know that when we have one exponent raised to another, that we multiply the exponents. There we go. And now I would do a really simple chain rule here. Number 29, notice we do have a quotient inside a squaring function. Notice that the numerator this time is more than just a constant. And so I am gonna set us up for the chain rule, okay? So in this case, I'm actually gonna start part of the derivative. Here's what I do when I see that I have two rules going on. I do see in total a composed function. There is this quotient inside the squaring function. So when I take the derivative of the inside function, I will need to use the chain rule because I have two rules going on. Sorry, the quotient rule. Because I have a chain rule and a quotient rule going on, I first write what I'm going to do. Here we go. So first of all, by the chain rule, I'm going to take the derivative of the outside function, the squaring function. The derivative of anything squared is 2 times anything to the first power. My anything is x plus 5 over x squared plus 2. I don't really need to show that one. By the chain rule, I will now take the derivative of the inside function right here. So that will be the quotient rule that you will use here, dot, dot, dot. You'll keep working. Do your math very carefully. Let's take a look at number 4. Let's do 107 A and C, and I assigned to you, B and D was what I assigned to you. There we go. So here's what they give on 107. They give you a list of x's. They give you the derivative of f, like they fill in the chart, and they give you on the rest of the chart different derivatives. So they're asking you for the derivative of g and the derivative of r. The derivative of g is a, the derivative of r is c. You have a b and d to do. So what do I do? Here's g of x equals f of x minus 2. Now, so what I'm going to do is they want the derivative of g, so I'm just going to take the derivative of both sides of the function. That would be the derivative of g equals the derivative of f, and the derivative of minus 2 is 0, right? Because it's a constant. So notice that the derivative of g actually equals the derivative of f. How can this be if they're different functions? Well, take a look at this. Let's say you have a derivative f, and you move it down 2. Okay, isn't it true wherever you draw a tangent line on f, if you simply move the whole function down for every single x, those tangent lines have the same slope, right? And so that's why the derivative of g is equal to the derivative of f. So how do I fill this chart in? Well, the derivative of g is equal to the derivative of f. So all of these values are the same. So of course we needed to do one where there would be a difference from the derivative of f. So let's take a look here. They're asking you for the derivative of r of x, and they're telling you it's equal to f with an input of negative 3x, okay? So they're asking me for the derivative of x. I do see that I have the function f with the function of negative 3x composed within it. I'm going to do the chain rule. I'm first going to take the derivative of f, evaluated at negative 3x. Remember, one derivative at a time. Derivative of the outside, not of the inside. And then I'm going to multiply that by the derivative of the inside function by the chain rule. So the derivative of r of x is equal to the derivative of f with an input of negative 3x times negative 3. So if it's okay with you, I'm just going to bring this negative 3 so you don't think it's part of the input up front there. We're going to place it where it's really working. So let's take a look. Let's put in, I'm going to use purple for this. Let's put in where x is negative 2, right? All right. So I'm trying to fill in this spot right here where the derivative of r, where x is negative 2, and we put our negative 2 in here. There we go. So the derivative of r at negative 2 is equal to the derivative of f at 6. Negative 3 times negative 2 is 6. So let's see, the derivative of f at 6. Oh, I don't have a 6. That's okay. It just means you couldn't apply it. Let's go to where x is -1. The derivative of r at -1 is equal to this expression. So the derivative of f at 3, okay? This is a -4. Right here where I underlined, -4 times -3 is 12. Let's move over to where x is 0. There we go. That is equal to, the derivative of r is equal to the derivative of f at 0. Let's go to there. Derivative of f at 0, that's a -1/3 right here, times a -3 is a 1. Let's move over to where x is 1. There we go. The derivative of r at 1 is equal to the derivative of f at -3. Okay, let me go there. -3, oh, I don't have where x is -3. That's okay, I tried. Let's go to where x is 2. The derivative of r at 2 is equal to the derivative of f at -6. Let's go there. Oh, I don't have a -6. Notice what will happen is if I put in a 3 here, I don't have that value either. I was only able to fill in these two. That's how you do that chart. Now on number 89, this is a good learning one. This is good for you, nice and healthy, okay? I had to give you plenty of hints because there's a lot going on here. All right, so here's my hints. I think I'm in the way. Determine the points from 0 to 2 pi where this function, 2 cosine plus sine of 2x, notice that's a double angle right there, has a horizontal tangent. Okay, a horizontal tangent. Horizontal means a slope of a tangent line where that slope is 0. And we know the slope of a tangent line is a derivative. They are asking you where the derivative equals 0. So they want you to take the derivative of this function, set it equal to 0, find where it happens. Well, there's a lot of things going on. You need a double angle formula. So A, find the derivative of x, okay? Now let me just say, let me go back. When you go to do 89, make sure that you've taken these notes and you follow these steps, okay? Find the derivative of this function. Then you will end up using cosine of a double angle to use substitution. Here's the 3 forms of cosine of a double angle. Remember, I had you memorize them. The best one to use is 1 minus 2 sine squared of x because you'll only have sine in your problem. Okay. Next, you are going to be left with a quadratic expression that you are going to need to factor and then set it equal to 0. Then you'll solve for the x's from 0 to 2 pi. This means you're going to need to know how to find angle measures given a trig value in quadrants other than 1. So you might want to draw yourself a little picture of the angle. Maybe it's 5 pi over 6. And what is the sign there? Okay. Then once you get those angles, they're actually asking you for the point where the derivative is equal to 0. So you'll have to take your x's, put it into your original function to get the y. So a lot going on there. Take these notes carefully. When you hit problem number 89, go step by step. Lots going on. And that's it. I hope you enjoy your assignment.
Enjoy.